Okay, well, I hope that you all are going to have a happy new year. I have been procrastinating making this video for a while because things have just been pretty busy on my end. It's been so busy, in fact, that I ended up busting my lip on a glass door today. So that's how my 2020 is ending. But hopefully yours will end much better. And so to begin, this is a paper that one of my friends had sent to me because he is interested in me trying to join the lab that he works for. And so what I want to do is go over this paper, which is just one of the three that he had sent me. And it's Aerosol Jet Printed Graphene Immunosensors for label-free cytokine monitoring in serum. So that's a mouthful of terms for, uh, they basically just want to make a way to make these cheap little sensors that are utilizing graphene, which is what would the word be? Which is electrically conductive, but that is also able to be modified with things on the surface of the graphene, which then helps it produce a signal. And by being able to produce a signal, you then allow for sensing of different chemicals. So, and what's nice about graphene is that you can chemically modify it, and then you can attach a lot of different biomolecules, such as antibodies, to these chemical modifications, and that way you can develop a robust repertoire of different types of sensors, really from starting from the same starting material, which is graphene or graphite, so pencil lead, really. So um, I want to, how do I phrase this? I wanted to study this a little bit more, but I made it a goal for myself to get this done before we start celebrating for the New Year's. So I'm just going to go into it. So let's begin. So Aerosol Jet Printed Graphene Immunosensors for label-free cytokine monitoring in serum. So here's the abstract. Graphene-based inks are becoming increasingly attractive for printing low-cost and flexible electrical circuits due to their high electrical conductivity, biocompatibility, and manufacturing scalability. Okay, so we need to break this down a little bit. So they're low cost. So graphene, pencil lead, it's everywhere. So if you are able to make an electrically conductive material out of this at a very, how to phrase that, and to scale, you can really make it for very cheap. So this is to be, what would the word be? You could contrast this against, say, like copper wiring, right? Copper is expensive. However, lead, really cheap, right? So if you can do it, or I shouldn't say lead, but graphite, pencil lead, very cheap. It's all over the place, right? So if you can do that, then you are really, what would the word be? I can't focus right now. It's New Year's. I've had a long day. But if it's going to be cheaper and better, and flexible as well. So if you are able to put this onto a flexible substrate and a substrate that you can bend over and over again, this could lend to something that is very effective at, say, putting inside someone's body indefinitely, right? So if you put it in someone's body and then it could monitor their vitals or monitor their biochemicals continuously, this could be very important or very useful, I should say. Anyways, and also this graphite is biocompatible. It's just a standard carbon compound that is not very reactive at all, and that's the type of qualities that you want to see in your biosensors. Anyways, conventional graphene printing techniques such as screen and inkjet printing are limited by stringent ink viscosity requirement properties and large as printed line widths that impede the performance of printed biosensors. And so there are issues with, say, whenever you have any type of printer ink or a lot of ink, there is a very narrow range of what types of viscosities you are able to deal with in that particular ink. So that is problematic when you want to have, what would the word be, have a lot of different graduate students working on this type of material or making these inks from scratch on the laptop or on the lab benches. And if you want to have reproducibility, you need to have at least some wiggle room as far as the properties of that particular ink are. So I could see this being a very problematic for people who are trying to develop different types of inks but then whatever ink they make does not fit into the narrow requirements of whatever machine that they are working with. So here they're saying that they're reporting that aerosol jet printed graphene-based immunosensors are capable of monitoring two distinct cytokines, interferon gamma and interleukin 10. So here they are using aerosolization of this particular ink, which could theoretically circumvent a lot of the issues that you would have with different viscosity differences and different properties of your solvent. There could be a technique that you could get away from all that by just making all these little nebulized little particles of your aerosol and then finding a way to focus that into a narrow range where you could basically print using aerosol jets. And so here they're looking at two different cytokines, cytokines being cellular signal molecules, the interferon gamma and interleukin 10. And so these, I don't know why they chose these two specifically, but I would presume that there is a likelihood that they chose it because of the pandemic that is going around right now, where interferon gamma and interleukin 10 are two cytokines that are very upregulated in the presence, especially in severe COVID-19. So, and granted, there's a lot of other different biomolecules that they could have chosen. And there's also a lot of overlap too, as far as a lot of different viral infections are going to have increased concentrations of interferon gamma and interleukin 10. Excuse me. But that's just my presupposition right now. So here, they're using interdigitated electrodes with 40 micrometer finger widths, and they were printed from graphene nitrocellulose ink on a polyimide substrate. So interdigitated, think of your digits, right? Your fingers are digits. And so interdigitated means that you have these electrodes that have a bunch of fingers that are interlocked with each other. And so this is one way that you can really increase the surface area between two different electrodes, especially if surface area is what you really want to have to increase your specificity or increase your sensitivity to whatever biomolecule you are looking for. And so they were printed from graphene nitrocellulose ink. So here you can see an example of this graphene nitrocellulose ink. You have your graphene sheets, which are coming from graphite that they have, I believe they might have sonicated it, but they'll go more into the methods down below. And here you can see the nitrocellulose. So here we have our cellulose polymer, and remember cellulose is a polymer of glucose chains. It's a beta 1,4 glycosidic linkages between glucoses, and a lot of the, or I should say all of the spare hydroxyl groups on the glucoses have been replaced with nitrosyl groups. Not nitro, so nitro groups, I think is what it is. Nitrocellulose, they're replaced with nitro groups. So here, this is an effective polymer, which when it goes through the heating process, when you are making these graphene sensors, this will actually turn into another electrically conductive polymer, which is useful for whatever they're wanting to do. So let's continue. And this is on a polyimide substrate. And so polyimide, just know that this is a polymer with a lot of different ranges. And so this is the chemical structure of the polyimide, what do you call it? The polyimide connector, I guess, is what you'd call it. So these interdigitated electrodes were annealed in carbon dioxide to introduce reactive oxygen species on the graphene surfaces that act as chemical handles to covalently link interferon gamma and interleukin 10 antibodies to the graphene surfaces. So here, annealing, you might have heard annealing in the context of metallurgy, where the annealing process is what's giving the atoms of metal more energy. And by giving them more energy, they are able to move their crystal structures around so that they are more malleable and more ductile and less likely to fracture. So when you are cooling metals too quickly from a liquid state, you could have a bunch of very small crystals, and having a lot of really small crystals can be problematic for the strength of the material, where it could be more brittle or more likely to break. Also, when you have been working metal too much and you are stretching and deforming it over and over again, you can actually be twisting those crystals around each other until they get smaller and smaller, and that can also cause brittle problems. That is, and annealing is when you bring it to a high temperature, bring your metal to a high temperature to help recreate new crystals that are more likely to have the properties of the metal that you would get if you were to get, I would say, a fresh piece of metal that you're just going to start working with. And it's in the state that you think it should be in order to have the properties that you want in that particular metal or alloy. Now, this is different from, say, dealing with graphene, where when you are annealing graphene, apparently, and I don't know all the details about this, I literally just Googled it when I was looking it up the first time, you're just putting it into an atmosphere of carbon dioxide. And so carbon dioxide is actually the most oxidized form of carbon that you can naturally get. And so the carbon in carbon dioxide, it has a lot of electrophilic properties. And so it has a propensity to want to steal electrons from something. And so when you have carbon dioxide dissolving in water, one of the ways that the carbon dioxide will grab onto electrons is it will actually steal some of the electrons from a neighboring water molecule, and this will form carbonic acid. And so by forming this carbonic acid, it's basically stealing some electrons from the oxygen, which then steals some electrons, more electrons from the hydrogens that are connected to the water, and that allows some of the hydrogens to leave as acidic protons. And so when we have rising carbon dioxide levels in the environment, you are also going to be experiencing more ocean acidification as a result of that, because carbon dioxide is very electrophilic and also very acidic, right? So this carbon dioxide, if you have a high temperature with your graphene, which is very rich in electrons, it's neutral, but it's carbon in a very reduced state. It's basically just plain carbon, ready to burn. It can burn easily, right? So it can partially burn by reacting with the carbon dioxide. And when it reacts with the carbon dioxide, it is producing these, I believe they say it is, I don't know if they go into the detail of what specific chemical group it is, but it's forming these oxygenated species on the surfaces of the carbon, of the graphene. And by creating these, you are able to then have a reaction take place so you can covalently bind these different antibodies. And here they are using interferon gamma and interleukin 10 antibodies. And so we would hope that these antibodies are specific, that they will only bind to these molecules, and they are, how do I phrase that? Yeah, well, I'll just say that they will only bind to their molecules of interest, and that they'll bind strongly so that they can develop a signal, whatever that signal is supposed to be. And so the resultant aerosol jet printed electrochemical immunosensors are capable of monitoring cytokines and serum with wide sensing ranges. So interferon gamma, you can have it between 0.1 to 5 nanograms per milliliter, interleukin 10, 0.1 to 2 nanograms per milliliter, and there's also low detection limits, these just random numbers, and high selectivity. So the antibodies exhibited minimal cross-reactivity with each other and interleukin 6. So interleukin 6 would be, I presume that they're putting this in here because that is probably highly related to interleukin 10. So the problem with a lot of these cytokines, and even the cytokine receptors, is that a lot of, or I should just say all biomolecules in general, will often borrow the components from other biomolecules. And so there are a lot of protein domains in some enzymes or in some proteins that will have very similar domains in a completely unrelated molecule, unrelated protein that's serving a different function in the body. And so the issue here is we have all these protein structures, and a lot of them are very closely related. And so we want to have antibodies that are specific to a particular biomolecule even though there's a very closely related biomolecule that could theoretically create some sort of noise in your signal, right? And so, anyways, without the need for sample pre-labeling or pre-concentration, um, moreover, these biosensors are mechanically flexible with minimal change in signal output after 250 bending cycles over a high curvature. And here the phi for this curvature is 5 millimeters. Don't ask me exactly what that means, but hence this technology could be applied to numerous electrochemical applications that require low-cost electroactive circuits that are disposable and or flexible. And some things that I want to see is this are these reusable, right? Because if you can have reusable sensors, that could be very important as far as lowering the costs, especially for medical equipment or finding things that you can just develop, make a lot of it, and then you can send it off to locations that might not necessarily have as much resources. So if they are able to utilize the same equipment for longer, that would be better, right? Anyways, should I keep on going? Yeah, let's keep on going. So the printing nanomaterial inks to create low-cost electrical circuits hold significant promise for a wide variety of applications, including medical diagnostics, food security, energy storage or energy harvesting devices, and electronic skinned or electronic noses due to their ability to be fabricated in a scalable fashion on flexible substrates. And scalable, very important, especially a lot of things that take place on the benchtop in a lot of university graduate student programs. There might be a lot of discoveries that take place, but if it cannot be brought outside of the lab, scaled up industrially, the economic impacts of those findings are much less likely to be very widespread, right? So this is, or I should say, much less likely to be impactful on society. So if you cannot scale it up, then it's less likely to be impactful on the way that you and I live. However, let's continue. I already lost my spot. Without the need. Where did I go? Yeah, in a scalable fashion on flexible substrates. So including those that are thermally and chemically sensitive, so paper or polymers. And they're doing this without the need for expensive clean room processing. So clean room, this would be expensive. So clean rooms are locations where you have to make sure that there's absolutely no dust, no nothing in the air, because even the slightest contaminant can completely ruin or destroy whatever you're working on. And so this has a lot of both applications for electronic development in general. So I presume GPUs and CPUs that are being produced right now, almost all of it has to be done in a clean room, because anything that can get into it can destroy the performance of whatever device that they are working on. So if you can avoid this with, say, a new technique, that could really lower costs and help contribute to the scalability of whatever product you're wanting to work on. So the infrastructure is important, right? If you want to scale up, you need to be able to put the infrastructure in place as well. We can't just be building clean rooms all over the place. So if you can develop a process that doesn't require it, all the more better, because then it is easier to get that infrastructure in place. So one of the more promising materials for printed electronics is graphene due to its high surface area. So this is very important. The more surface area you have, the more likely I shouldn't say more likely, but the more abilities you have to do chemical modifications and you can do more chemical modifications, and you can do more, you can have more sensitivity to whatever compound that you're wanting to work with, because the more surface area you have, the faster the chemical reactions can take place. So with the high surface area, you can more quickly get the signal that you want to have. So you can have that, and also the chemical stability is important, especially if you want to reuse things over and over again. So the graphene, important for that. You could see issues with if you use, say, some metals that could corrode easily, having the reproducibility even after only a few cycles could become an issue, right? Anyways, mechanical flexibility and biocompatibility, both of these go hand in hand. If you do not have mechanical flexibility or biocompatibility, the ability to produce sensors that you could put into someone's body is greatly diminished because, lo and behold, your body is squishy and your body is bios, right? So if it's not compatible with the bio, you're screwed. So chemical vapor deposition has been a traditional fabrication technique for graphene-based devices. And so chemical vapor deposition is when you take whatever material you want to work with and you vaporize it. I believe it's usually done in a vacuum, and then it deposits itself on whatever surface that you want it to deposit on. And so for graphene, this was a very popular traditional technique. However, this graphene synthesis process and the associated techniques necessary to incorporate the resultant graphene into devices, this has limited the wide-scale use of chemical vapor deposition graphene for electronic devices. And the reason why is because this is a tedious process. It's not very scalable. And if it's not scalable, you're going to see it's going to be limited in its ability to show itself in the industrial applications, right? For example, CVD processing has high energy costs and low yields due to the use of high temperature and low pressure furnace synthesis protocols. So yeah, if you have to create this vacuum, and if you have to create really high temperatures to vaporize this material in the vacuum, that's all expensive, that's all energy intensive, and if we can avoid that, the better, right? Moreover, the subsequent graphene film transfer process needed to relocate the graphene to a more electrically and electrochemically inert substrate is tedious and can significantly damage the graphene film. So the problem here is you produce your graphene, right? And so after you produce your graphene, you need to put it on whatever substrate or whatever material that you want it to finally be on in the final product, right? And if that material is not something that you're doing this chemical vapor deposition on directly, that process of moving the graphene from one area to the other can cause damage, and that can lower reproducibility, which is not something that that's of high importance, right? Especially for any type of sensor, you need reproducibility. So finally, additional patterning steps through photolithography are required to fabricate CVD graphene devices over a large area. So I believe photolithography is when you are using light to either damage or strengthen certain areas of a particular material. That way when you do an etching or a wash later, you can actually leave behind different patterns based on where the light has hit. Anyways, a more scalable method of obtaining graphene is through liquid phase exfoliation of graphite. So this method produces graphene dispersions, which can consequently be formulated into graphene inks for a variety of printing applications, such as screen printing and inkjet printing for large-scale manufacturing. Conventional screen printing that uses a squeegee to force ink through patterned perforations on a metal stencil typically result in low-resolution circuits. So screen printing, this is how a lot of shirts are developed, right? You basically will have the material, and then the places that you want ink to go through the material for, rather than it being solid, you actually have a screen in that area. And so where that screen's at is where the ink is able to perforate through the material. And so when you have screen printed shirts, usually it was a solid material that had areas with screens on it. And so this is a way, and the reason why you would use a screen rather than just an open hole is if you have an open hole, that could affect the integrity of a taut surface area. So if, let's say, I can't really describe it very easily right now, but let's say this was your screen, right? And let's say you wanted to have a giant X through it. Okay, well, this is not going to work out very well, but let us go. So let's say you had a giant X in it, and you were pulling against it, trying to pull it straight, it could be that since you have this entire area and, sorry, doing this backwards, and this entire area completely removed, then it would be very easy for this to bend in ways that it's not supposed to. But if you leave a screen in that open area, then it can maintain some of the rigidity, and then as a result, you can have the screen print available. Sorry, that was an explanation that didn't need to happen. But with this conventional screen printing for graphene-based inks, it's very low resolution. You can't get the minute details that you need really to have, say, high surface area and have more specificity and what would the word be? Not selectivity, but sensitivity to whatever material or whatever molecule you're trying to detect. Anyways, conventional screen printing uses a squeegee, and more recent advances in screen printing has realized high resolution circuits, so 3.2 micrometers, through the use of lithographically patterned composite silicone molds. So, however, since the fabrication of these high-resolution stencils requires clean room processing, for example, photolithography requires a clean room, and reactive ion etching, these are not compatible with high throughput. High throughput meaning you are able to do a lot of it or push a lot of it through. These are not compatible with high throughput conventional screen printing instruments, and so you can't scale this up easily. And if you can't scale it up easily, it's not going to have a huge effect on everyone's day-to-day life. So inkjet printing is a scalable printing process compatible with roll-to-roll processing. Indeed, we have recently demonstrated that inkjet printed graphene electrodes can be used for electrochemical biosensing, such as hydrogen peroxide sensing and ion sensing in sweat. However, due to the limited spatial resolution of high-throughput inkjet printing, say that 5 times fast, these biosensors have been limited to macroscale electrode designs that can be functionalized with enzymatic and ion-selective membranes for subsequent amperometric, so amperometric meaning measuring the amperage or measuring the current that is flowing through, so subsequent amperometric or cyclic voltammetric sensing modalities. And just know that cyclic voltammetric sensing is it's basically when you're scaling through different voltages of whatever circuit you're dealing with, and at different voltages you will get different currents flowing through. And so as you go through the cycles of voltages, you will basically have very, very little current, and then there will be a period where you will actually go up in your current when it's breaking that barrier and allowing the current to flow more easily. And then it will as you go back, then it will also go back down. But I don't know all the details. That's something very physical, but you can look it up if you want to get a little bit more of an understanding about it. Anyways, these macroscale electrode geometries are not well suited for high resolution impedance-based measurements often performed with interdigitated electrodes, or IDEs, fabricated on the micron scale and functionalized with affinity-based biorecognition agents such as antibodies. So these macroscale electrodes, the geometries, the way that they're structured, are not well suited, like the interdigitated electrodes, for this chemical processing where you add these biospecific molecules to them. And so these other techniques aren't necessarily the right geometries in order to do these sensors. And so the interdigitated electrodes seem to be one of the better types of geometries necessary to have these types of sensors take place or be produced. So moreover, the favorable IDE properties such as high signal-to-noise ratio, the fast response time, and that fast response time probably has something to do with the high surface area, so the reaction takes place quickly, and favorable reaction diffusion kinetics improve as the IDE finger comb geometries are decreased to a scale of 10 microns. So as you are decreasing the IDE finger comb geometries, you are getting better properties in your particular sensor. So In order to attain such a high line resolution with printed electrodes, researchers have begun using various hybrid printing techniques that require pre- and post-patterning steps such as inkjet maskless lithography. These words will get you tongue-tied very quickly. So inkjet maskless lithography, selective sintering, and transfer printing. I don't know what sintering is. Let's look up what this is real quick. Selective laser sintering is an additive manufacturing technique that uses lasers as the power source to sinter. Oh, okay. So if you have a powdered material that you place on the surface, you will have a laser that will go down and basically superheat that very specific area, and that is a way that you can have these that is a way that you can basically print these structures basically by melting whatever substrate or powder is below it, and then I presume you blow away the powder when you're done. So what does sintering mean? Melting? Or frittage is the process of compacting and forming a solid mass of material by heat or pressure. So, okay, so when you really heat this material, you can fuse it together by basically just adding a lot of heat very quickly. Okay, well, you learn more every day. So with the selective sintering, you can make these structures, and transfer printing. So for example, high-resolution inkjet printed patterns require an additional sacrificial layer that is used in a lift-off patterning of graphene or used as a deposition adhesion promoter. While these techniques can produce high-resolution conductive traces, so 20 to 60 micrometer line widths, the additional patterning steps complicate a roll-to-roll manufacturing process. So other high-resolution inkjet printing strategies rely on the fluid dynamics of the coffee ring effect, which can create 5 to 10 micrometer wide conductive traces or sub 10 micron channel lengths between printed features. But possible device geometries are still limited by the droplet radius and drawing patterns, or an additional lift-off process that makes the technique less scalable than the inkjet printing alone. Therefore, a need exists to create high-resolution graphene biosensor circuits that are compatible with high-throughput manufacturing. And so this is where the aerosol jet printing comes in, or AJP. It is a direct write additive manufacturing technique that eliminates the need for masks, stencils, or hybrid techniques to produce pattern circuits with high spatial resolution. So the more steps that it takes to get your final, I would say, shape, the more steps necessary, the more likely that you are going to introduce error into the production of the final product. So if we can avoid having to stick things to each other and then rip things off and try to transfer things from one surface to another, if we can avoid all that, that is going to be better and be beneficial for the reproducibility of that product. So what I'm going to do is, we're already at 33 minutes, so I'm just going to jump into what is going on here. So here they have developed one of the inks, and so this is an ink that has the graphene. They put in the graphite in originally, and then they will mechanically agitate it, I believe. And they mechanically agitate this in acetone, but then they also use this nitrocellulose, which, remember, this is the cellulose. These are the nitro groups that are replacing the hydroxy groups on cellulose to create nitrocellulose, an old form of gunpowder, if I do remember correctly. Explosive. And anyways, this is going to be one of the, not the dispersion agents, but one of the, I'll just say that, one of the agents used for surfactants. It's going to be one of the things that helps keep the graphene in solution. And so here they decided that it was good to use a solution that has a little bit of the dibutyl phthalate. So here we have the phthalic acid, which, if we're not aware, phthalic acids are dicarboxylic acid benzenes. So here we have your two carboxylic acid groups that are connected to a singular benzene. And so this entire thing is a phthalic acid. And I should look to see if they need to be right next to each other to technically be a phthalate. I don't know all the jargon, right? But here we have dibutyl phthalate, and so this is one of the dispersion agents, and then or stabilization agents, and then another one is the ethyl lactate, and so here we have our lactic acid group, which lactic acid is what your muscles produce when it's gone anaerobic, right? So here we have lactic acid, which it has an ester group with ethanol, which is alcohol that you drink, right? So here's ethyl acetate, and so these two help stabilize the graphene in the solution. And so what I'm guessing, and this isn't gospel at all, I'm just sort of guessing what is happening here is with the phthalic acid. So for those of you who are not aware, phthalic acid, or I should say aromatic molecules in general. So graphene would be an example of an aromatic molecule. These benzenes groups are aromatic as well. These have the property in that their pi orbitals are going to exist above and below the plane of whatever molecule, whatever aromatic molecule you have. And so here with graphene, if you have a sheet of graphene, the pi orbitals are actually going to be sticking above and below the graphene sheet. And so this is going to be locations that are rich in electrons, and that can be suitable for having certain bonding interactions with neighboring molecules. And in fact, graphene sheets like to stick to each other because these pi orbitals will do what is referred to as what is it? Pi bonding? Wait, pi stacking, sorry. Pi stacking. Let's get this up for you. So pi stacking is when the pi orbitals of aromatic molecules will interact with each other. And there are different ways that you can have this pi stacking, but to me the most common way is, or to me the thing that sticks out to me the most is when you have the sandwiching effect taking place. So basically you have two molecules, both planar, and the pi orbitals are sticking on above and below the planes, right? But if they're sticking above and below, you can have two ends that come together, and then the pi orbitals that are sticking out on one side of each of them will come together and interact in a particular way. And in fact, this is one of the ways that helps give DNA its shape. So your DNA will have pi stacking take place on the aromatic bases of the DNA, so the A, T, C's, and G's, those actually will have pi bonding with the base that is below it and above it. And this actually helps compress the DNA together. And by compressing it down, that actually is what's causing the twist a little bit. So this pi stacking is actually bringing those molecules or bringing those bases closer together. And in order to bring them closer together, there actually has to be some twisting that takes place on the backbone. So we'll just look up DNA. That's not a good one. Let's use. So here you can see you have your pyrimidines and your purines. These are the bases. And here we actually have aromatic rings right here. And so here, this aromatic ring is going to exhibit not just the hydrogen bonding with what's on the other strand of the DNA, but it's also going to experience some pi stacking with what is going on below it. And so this pi stacking that is taking place in between these aromatic bases are actually going to require the twisting of some of the twisting of the backbone in order to allow it to move together a little bit more closely. So just that is another side thing. Well, anyways, what I think might possibly be happening is that this aromatic ring right here might theoretically be undergoing pi stacking with the graphene to help stabilize it and prevent them from amorphously coming together right away, and basically help keep it in a suspension for a longer period of time. And so this dibutyl phthalate, later in the paper that it talks about it a little bit more, this dibutyl phthalate actually has a really high boiling point, and its high boiling point helps the ink stay a liquid as it's being aerosolized. And so it gets aerosolized, and then this ink, which is aerosolized, gets pushed through this aerosol jet printing nozzle, and this nozzle will have the carrier, and it will have two sheets of more gas that help direct all the ink into a very specific area. But this process will require a solvent that doesn't evaporate very easily. And so that's what this dispersion agent or the stabilization agent is doing. Since it does not evaporate unless brought to a very high temperature, because it doesn't evaporate easily, it's going to help maintain the liquidity of that aerosol. And so what I think is also happening here is, since it's phthalate, these carboxy groups are actually going to be withdrawing a lot of the electrons from this benzene group. And so the electrons that are being withdrawn from the benzene group is going to give it a partial positive charge. And so pi stacking is even better when you can have opposite charges of your rings. And so graphene being neutral, those pi orbitals are going to be very electron rich, and so it's going to have a partial negative charge. However, for phthalic acid and this dibutyl phthalate, these carboxylic acid groups are actually going to withdraw or steal a lot of the electrons away from those pi orbitals. And by doing that, it's going to make it much more positively charged, which can help with the pi bonding interactions. So that's what I think is happening. Who knows if that's what's happening, but it's going to be there and exist until they undergo a dehydration or a heating process, which drives this phthalate out of solution. But anyways, we are using this to create these interdigitated electrodes, and here you can see these digits that are intertwined with each other, and they're on two electrodes, and they're on this polyimide film, which is in orange, I believe. And what they do is they will take this, they will put it into an annealing process to add some different chemical modifications to the electrodes or into the digits. And by adding those chemical modifications, they are then able to attach these antibodies. And here they're using an antibody for interleukin 6 and an antibody for interferon gamma. And so they are able to attach these antibodies to this graphene. And then they also have to add a blocking agent to help prevent just random stuff from sticking to the unbonded parts of the graphene. But then the benefit of this is you will then have your antibody, which is now on your electrode, and then if it binds to its antigen, which would be the interleukin 6 or the interferon gamma, once it binds, it will actually create a signal, and you can measure that signal because then the amperage will change for a given voltage. So, what else? I think I should stop here because I got to start celebrating. But I'll do another video with more on this, thinking what I think should change, or not necessarily change, but where I would go with this, because I think that there is a lot of potential here for creating screens, I think. So if you can create, you know what, I'm going to save that for the other video, because I have a few ideas that might be good for creating very good diagnostic techniques or more diagnostic related stuff. So with that, I'm going to head on out. I hope you all have a good new year. And sorry for stumbling through that. I had a little bit to drink. Not a lot, but a little bit. And I'm tired. So Happy New Year. I hope this upcoming year is going to be a lot better for you than this year was. But it looks like things are on the up. So have a good one. And hopefully I will see you tomorrow.